afternoon, everyone. No? And 1 o'clock is an unholy hour, and I hope that you have been filled in the lunch. And I would like to make my talk as interesting as possible because 1 o'clock is considered the holy grail, no? In the Philippines. So my talk is about Python-based high-level synthesis for programming field programmable array using MyGen and MyHDL. And I hope you are not turned off by the technicality of the title because looking at it, it seems to be quite technical. No? But field programmable arrays are actually simple devices, and they are considered to be watch-on compared to the existing microcontrollers that we are using. Okay, so again, thank you for the introduction, but I would like to introduce further what I do. I'm a university professor, but I'm more into designing systems, embedded systems. And I'm a design thinker, and I also would like to create projects that geared towards startups. So for my students, I always tell them to do research, but make sure that the research that you're doing is creating something that impacts the society and somehow change the projects that you have into something that can be scalable and commercialized and impacts the society. I'm also a startup founder, and most of my startups are in the blue economy. That means in the marine space, because I consider it a niche wherein very few has fared, no? Because of the challenges of the sea. Okay, so based on this also, I have used Python, both the desktop and MicroPython, which is the embedded systems, in developing these projects. So we start off with a tagline or the question: customization is the driver of innovation. Would you agree? Anyone? Do you agree? When we talk of customization, what is customization? The ability to customize, the ability to control things your way, the ability to create. And I think customization is the key for creating great products, no? And sort of like creations. So we start off with the difference between software and hardware. So any idea what's the difference when we're talking about computer science or computer engineering, and also in computer field? We are always bombarded with these two terms, which is software and hardware. So what the heck is the difference? No? So if you look at the screen, this is actually the mainframe, the ILIA computer back in 1970s. So to run this computer, you need to have a very large room in order to run it. But again, it came 1980s. Okay, this large room was replaced by, of course, our integrated circuit. Now, if you look at the evolution of the hardware, it's quite striking, no? That very large building in the past created for computers is now just a tiny bit of chips. And so that our cell phones now contains the equivalent of a big building way back before, no? In terms of hardware. So we talk of hardware, it's the physical thing. It's the circuits, it's the gates that form your hardware. Now, how about software? So I have here a diagram wherein I have 4 hardwares, no? Which is considered an adder circuit, a subtraction circuit, a division circuit, and a multiplication circuit. Sort of like a 4-operation arithmetic logic unit. No? And this is implemented in hardware. So circuit A is for addition, circuit B is for subtraction, and I have 2 numbers, A and B. So to perform the required operation, I have 4 switches. And if I want to perform addition, I switch the one on the output of the addition to perform addition. If I want to create subtraction, I will turn on the switch to perform subtraction. And if I want division, then the result will be this. Now, if you can imagine this is how we implement our calculator today. You can imagine there will be thousands more of switches, no? But again, in calculators, you only have a few switches. So this is hardware implementation. Addition is implemented using gates. Subtraction is implemented using hardware circuits, physical circuits. And because of that, we have a very bulky circuit to create that one. But again, the operation of arithmetic is done through hardware. No? So we call this the hardware-based system. However, we can actually program the hardware, convert it into sort of like electrical signals. It's stored in the memory. So the addition can be implemented by just a statement like C equals A plus B. Then subtraction can be C equals A minus B and C equals A over B. Okay? And then instead of having 4 hardware, what we have is we only have one physical hardware wherein we customize it. So this single hardware runs 4 operations: addition, subtraction, multiplication, and division. So this is now the concept of software, right? We use a hardware, but on top of the hardware, we run software. And this software is the equivalent of addition hardware, subtraction hardware, division hardware, and multiplication hardware. So software and hardware actually means the same thing. No? So, and when we talk of software and hardware, hardware is actually costly, while software is cost-effective. Okay, and then hardware are faster compared to software, so they have their limitations as well as the pros and cons. But the good thing about software is you can minimize on hardware, and eventually you can minimize on the costs. And that is what is done in our computers. No? The computer, if you're going to look at it, it's made up of software, but if you're going to translate into physical hardware, that will be thousands and thousands of hardware. Okay. So software has drastically reduced computer size. So in the 1980s, 70s, we have these large mainframes because everything is implemented in hardware. But then due to the advent of computer, we have the desktop, and it became smaller. And today, by today's standards, we now have miniature devices. All of this is because most hardware is now replaced by software. But again, software is just equivalent to hardware, right? So hardware is hardware equal to software. So in Python, this is the equal sign, right? So this is implemented. Is software equal to hardware? And you can say true or false. So in the implementation, of course, they are not the same, right? So in hardware, you need to have physical devices, but in software, all you have to do is memory. But in terms of functionality, the equality is true. Software and hardware perform the same thing, right? But in terms of cost, this equation or this conditional, this Boolean expression is also false because hardware implementation is more expensive than software implementation. Okay? So what does this mean? Because if you're going to implement systems in hardware, you can see something there on the screen. You can have a lot of chips. And if you're going to prototype it, you know naman, if you're going to do the breadboards for this, you will come up with spaghetti wires. So it's quite, you know the drill, right? If you have done this in college, that's a pain in the mind, right? So hardware implementation is usually tedious. And we have traditional embedded hardware. So I think most students are familiar, even hobbyists are familiar with this. We have the Arduino, we have the STM32, we have the ESP32, we have the Raspberry Pi, and everything. So these are off-the-shelf microcontroller board wherein you can program. But they have their limitation. What do you think is their greatest limitation for this one? If you have played with Arduino, what do you think is the most limitation? What's its limitation? Even the Raspberry Pi has its limitation. Okay. So sometimes when you use this board, how you wish that it has this feature, how you wish that it has this feature, how you wish that this board has this peripheral, how you wish that this board has this other peripheral. So we buy third-party modules to implement this I/O. No? So that's the main limitation. It's limited to customization. So what you have there is just the board, and then you can just program it based on its own assembly code and C++ or its own language. There's no room for customization. In that case, your software is now dependent on the physical hardware. Now, what if you'll be able to have a board wherein you can customize everything up to the hardware level, up to the gate level, up to the transistor level? Is there such boards? So we introduced to you SOICs, ASICs, and FPGAs. So system-on-chips are application-specific integrated circuits. So from the word application, so this circuit is designed from the ground up for a particular application. So if you're going to have a GPS chip, then its application is on GPS navigation. If you have a accelerometer sensor, then its function is IMUs. No? Okay. So chips are created specifically for a certain application, and they come in that specific application. So again, there's no customization. But then we introduce the field programmable gate arrays. So what are they? So from the word field programmable, it can be reprogrammed when it is deployed. So that means it can be customized even if it's released to the market or to the wild, right? And if you look at the closer look at FPGAs, for example, this is the Altera Flex. What you find inside are actually series of logic elements. So in other words, these are logic blocks which are not connected from one another. So we have 1,000 logic units or 3,000. Modern day FPGAs up to have even 1 million logic elements in them. And the good thing is they are not connected yet. So therefore, you can design your blocks, your design, and then program the interconnects to perform your specific function. So FPGA is the king of customization. If you want to develop your own chip, the way you want it, what you really want it to do, then FPGA is the way to go. Now, how are digital chips developed? No? So in the old ways, we have the logic gates. Then we connect it via the breadboard, and then we have the wires, no? The nightmares in the wires. And then we manufacture the prototyping board using chips. And then finally, we manufacture the developed IC using a wafer. But the problem with this is when you have the wafer mask, it's very expensive. So when it's already done in the foundry, there's no more room for you to change the layout of the circuit. So that's the main limitation. And you need millions to produce the wafer. But today, we design digital chips using the standard model. So first, we specify first what the function of the circuit is. Then we do the functional design. And then we do the synthesis. Synthesis is from functional design. We synthesize it, wherein we create the gate level implementation. And once we have the gate level implementation, we route it inside the chip. That means we connect the wires inside it programmatically. And then we verify if the system works. And if the system works, then you can then fabricate the SOIC. But fabrication will require millions. So in order for you not to invest on that, so field programmable gate arrays are available in the order of $1 or $2 per piece. So it's highly customizable. And the good thing is you can name the chip yourself because you're the one who created it, right? So this is quite exciting. No? You now have the power to create your own chips. Okay, but the question is how? So we create programs or we configure FPGAs using what we call hardware description language or HDLs. No? So HDL from the word hardware description, it's a text-based script wherein it's not similar to a program script. No? But here you have a text-based file, but this file actually describes what a physical hardware is. So for example, sir, if you're familiar with the gates, you saw here this is actually the 1-bit adder, wherein inputs A and B, which are digital, is connected to an OR gate and an XOR gate. Okay? And the S is actually the sum of A and B, and then C is the exclusive OR. Okay? And you have the truth table. Now, if you look at the the HDL code, we have the keyword module. So this is the name of the other. Module is like an object. And it has the following ports: inputs A and B, and outputs S and C. No? And then the implementation is S is equal to A and B, and C is equals to A exclusive OR B. And we have N the module. So in this case, this HDL is a description of the physical hardware. So that's the concept of hardware description language. So we have two flavors. We have Verilog and VHDL. So these are the industry standards in describing digital hardware. No? And if you look, this Verilog is similar to C, whereas VHDL is quite verbose. But again, in terms of it, it has a same construct like the ports and the assignment. No? Now, but again, if you're going to analyze this, did you understand the code? Yes, right? But if I'm going to give you another option, how about this? Do you understand the code? Much better than before? Yeah. This one is generic VHDL and Verilog, but this one is, of course, Python. No? So this is Python. So MyGen and MyHDL and other open source libraries are actually wrappers or generators of HDL, which is the standard. So MyGen and MyHDL are libraries wherein you can generate VHDL or Verilog code. Okay, and then you start with Python. Okay, so as you can see, we have a class which is 7 segment, and in here we have an example which is an object of a 7 segment, and then we then generate the VHDL. MyHDL similarly is 7 segment control. So these two are almost the same, but they differ in implementations. So the good thing is you can now use Python to develop your VHDL code. Okay. So for example, we have here. Okay, so this is a MyGen file. So if I'm going to run this, okay. So if you look at the output, it produces the Verilog code. No? So from Python, it is now converted into a Verilog code. Similarly, for this MyHDL, so this will also generate the Verilog code. So why do we need to generate the Verilog code? Because standard FPGA program or standard FPGA commercial development will always start from the standard, which is VHDL or Verilog. But for us Pythonista, of course, we would love to have Python as our starting point. So usually, if you want to new into VHDL or Verilog, then you can actually start with the MyGen or my VHDL for you to, because it's much more understandable as Python programmers, no? Rather than the Verilog. No? Okay. Okay, so of course we will not delve deeper into this. No? Just look at the repository for MyGen and my VHDL. Now, of course, I would like you to also see the FPGAs in action. So supposed to be we have an FPGA that is connected to a switch. Okay, and then we have a servo motor. So I'm going to demonstrate an application to be as simple as possible. I choose servo motors because I think it's the simplest one. So you have here a FPGA board. So this is from Altera. Okay, so this is composed of 240 logic elements. So that's how many logic gates it's involved. No? And I have here an application for this application. So I have a servo motor connected to one of the IOs, and then I have a switch. So this has been pre-programmed so that I can demonstrate it. So if I'm going to press the switch, so it will turn, right? So the switch actually turns the servo motor. And this is now the configuration of the logic gates inside it. So if I want to change the application, then I need to reprogram this. So the programming here is up to the gate level. Okay? So let me show you how it is done. So this is Quartus from Altera, and other vendors also have their own development. But again, these are all free. Now, the good thing about FPGA development, our tools are free. So here you can see the generated Verilog file. This is actually MyGen generated. So I started from MyGen, and then this generates the Verilog file. So once you input that in your tool, the next thing is you then compile that one. Okay. So compilation is the process wherein the code is converted into logic gates, physical logic gates, and implemented inside the chip. Right? So it's running. Okay. So quite slow. But anyway. So once it compiles, the next thing is you can actually download it. Okay. So anyway, it's still compiling. But so after compiling, you then actually assign the pins. So for example, here we have 3 pins, the clock, S1, and servo. And this is the physical layout of the FPGAs. So the good thing about this is you can change the location of the switch. For example, I can put it on gate 16, or I can put it anywhere in this field, right? Let's see if it's already compiling. Yeah, we finished compilation. So after the compilation, the next thing you do is go to the pin planner. So this is where you assign pins. Okay. So I assign my clock and S1 and servo inputs to these physical pins. Now, the thing about this is you can actually see what's inside the FPGAs. No? So how do we do that? We go to the netlist viewer. So okay. So this is the generated physical circuit. Okay, and if you're going to open what's inside, this is another. Actually, the implementation is we have a D flip-flop, and then we have another D flip-flop. Quite simple. No? Now, how did they map this inside the chip? So you can actually view that by looking at the technology map viewer. So this is what's inside the chip that is being generated. No? Okay. And you can actually open the contents of the circuit. No? Okay. And you can customize it. No? So those gates are actually on your control. No? Okay. And we can also view the post-fitting. Post-fitting is how the system is being implemented after the synthesis. So the text-based Verilog code is converted into this physical circuit. So this is what's inside chip, what is being formed. Okay. Okay. So we have implemented this application, and if I want to change this, I can change the parts. So the good thing about FPGA is you can control the pins. You can customize it as what you want, or even one. So good thing for maybe you can develop chips or processors. You can build your own processors. You can build all your peripherals. Sort of, you can build your own Arduino if you want to. So there are IP cores which are for processors. No? So why is FPGA development important? Because the future of programmable chips is actually now. So if you look at these vendors like Intel, Microchips, ARM, or NVIDIA, NVIDIA is the one that resonates to us. They are going into the industry direction. What do you think is the most exciting field in the industry today? So it's AI. No? So these companies are going after, and you know NVIDIA is doing that. And the future of programmable chips is AI embedded. So that means there's a way wherein you can embed your models. And the good thing to do, and the one that's particularly useful for that, is your field programmable gate arrays. Why? Because it's cheaper compared to the CUDA of NVIDIA or the Jetson Nano Okay, the Jetson Nano will cost you around 5,000 to 6,000, while FPGA chips like in Lattice will only cost you 600 pesos or 500 pesos, or in English, $10 or less. And you can broke as many as you want because you can buy one. And of course, mainstream AI frameworks like PyTorch, TensorFlow, for those guys who are into machine learning like TensorFlow, the good thing is there is TinyML. TinyML and TensorFlow Lite is a framework wherein you can convert your TensorFlow model or PyTorch model into an array that can then be converted into Verilog and then be baked in the field programmable gate arrays. So the good news is your models can now be deployed in edge devices. So think of something like an FPGA which will run your TensorFlow model or your PyTorch model, and you can deploy it on the field, even without the internet, right? And that is what these guys are also doing. So, what digital chips do you want to make today? Okay, so if you want to build more, then FPGA and programmable chips is the way to go. So I hope I have trickled your imagination on the next thing that you're going to do and create. And sadly, field programmable gate arrays are not that popular yet in the Philippines. But it's the industry standard that is being used in the design of digital systems. Okay. So again, thank you very much. And if you have any questions, I feel free to answer.
Hello. Can you hear me po? Hello?
Yes.
So, in the one part that intrigues me po is the fact that you mentioned that we can embed our AI models into the programmable chips,
Yes.
right? So, does that mean the size of the model is no. Does that mean the chip, the strength, I don't know if that's the right term, the strength or like the power of the chip is proportional to the size of the model. So, if I have a bigger AI model, does that mean I need a stronger chip in order to embed it?
I think not. Because the way to go, if you're going to, when we do machine learning, and if you're going to generate your model, actually it's very resource intensive in the training phase, if that's a machine learning system. Diba? So you need a very powerful computer, a very fast computer to train it. However, when the model is already trained, it is actually just a series of weights, and that can be converted into array. A small array, actually. And that can fit into small ROMs in the chip. I think it's virtually not that big when it's already done in training. And the good thing is also these chips are composed of even thousands of logic elements. So, kayang-kaya niya yung it can carry the model. So, it's up to you lang is you train it. Yeah.
I have another question po.
Yes.
So, another one that I want to ask for is in terms of energy usage. So, how efficient would this be compared to like having a separate device that's running on a GPU?
Yes. So the good thing about this is also you can conserve power. So the bad thing about microcontrollers is you have peripherals that runs even if you don't use it. For example, the analog to digital converters or the timers. If your application doesn't use them, they are still powered. But in FPGA, you can turn off the other gates by yourself. Actually, this is much more power efficient compared to standard boards. So as I said, customization is the thing here. You can even customize the power consumption. You can even change the routes of the signal so that it can be fast. And the good thing about FPGA is it runs in the cycle clock. So if you have 1 gigahertz clock frequency, then it runs in 1 gigahertz clock frequency for your application. Yeah.
Thank you po.
Okay, so I hope that answers your question.